Okay, here's another common way to think about how to complete reactions. It's not only training you on the reactions that you're supposed to know, but it's also training you on the beginnings of synthesis. And so this one really is trying to get you in the habit of thinking backwards. Now, in this case, I have a reagent and I have the reactants or the products. And so I don't have to think that hard. I know what is happening in the reaction. So all I have to think about is what is the reactant that made that happen. Now, for the first case, I'm going to start off with something that's got 1, 2, 3, 4, 5 carbons. And so I know my reactant will have 5 carbons. And I've got an alcohol group, and it looks like it added in the second carbon. And so I have a choice here, right? I'm going to have a double bond somewhere in my 5 carbon reagent. 1, 2, 3, 4, 5. And I have a choice. I could have had a double bond here, or I could have had a double bond here. Either of those two possibilities will result in an alcohol adding in the location that it did. Now, let's take a look at the reaction. The reaction is oxymercuration, demercuration, and that adds alcohols, or it adds the nucleophile in the reaction. In this case, the nucleophile is water. It adds that Markovnikov. So it adds it in the more substituted location. And so we always want to pick the reagent or the reactant that would lead to the most efficient reaction. So if I had a double bond here, would I get the product? Sure, but I would also get an equal amount of product that had the alcohol at this location, and that's not what I want. So this bond is the preferred location to have the double bond because it will lead to only the product that I want. It's a more efficient answer. Okay, so again, just to recap, if you chose the double bond in the other location, you would only get partial credit. Choosing the double bond in this location gets you full credit. All right, so what's the next thing that's going on? This one should be fairly straightforward because there's only one reaction that forms double bound oxygens. This is ozonolysis. And so I think it's pretty reasonable to help the student predict what's going on with this reaction by saying, look, remember that ozonolysis actually breaks the double bond. And what it does is it splits that double bond. That double bond, it splits it, it breaks the double bond and it splits it, but it doesn't change it. It doesn't change it. So I split it. I moved this piece that direction. I moved that piece that direction. And so I actually end up with 2 products. The only thing that happens is that I add an oxygen right there. So to go back the other direction, what I do is I identify these double bonds. And I say, okay, let's get rid of the oxygen. And then what I want to do is I want to reconnect the double bonds. And so I'm going to have a double bond here. And I'm going to reconnect it with the other piece. And that other piece looks like this. And so there's the starting material. Okay.